Hello everybody, my name is Keiyu Kawai. I'm working at Ehime University in Japan. Today I'm going to talk about assessment of water absorption in concrete member by electrical resistance tomography. Let me introduce introduction of this study. In Japan, water exposure in which water is supplied to concrete by wet and dry actions and rainfall has been considered for the durability assessment, especially on carbonation-induced corrosion. Many studies have been carried out for examining the ingress of water on the corrosion processes in concrete. When concrete structures are carbonated, the corrosion may not be severe unless water containing dissolved oxygen is supplied to embedded steel bar. The effect of water supply may have a significant impact on the durability performances with regards to corrosion processes of steel bars when carbonated. This study is aimed at developing a new technique for assessing the ingress of water applicable to actual concrete member. ERT is a technique which allows us to assess the changes of electrical conductivity in electrolytes. This has been extensively used in medical geophysical applications. In recent years, the ERT has been studied for visualizing variations of conductivity in concrete specimens. The ERT system is typically carried out in such a way that DC or AC current is injected to a pair of electrodes among 16 electrodes equally apart located in cylindrical object, and potential differences are measured between each adjacent electrode as shown in the figure. More recently, unsaturated water flow through pores formed in concrete has been intensively examined through ERT systems to visualize the permeation front that gradually changes with elapsed time. This study examined the ERT assessment for water absorption in concrete prism specimen, which is not typical application of ERT system. This study examines absorption of water in the cross-section of typical concrete member 330 by 330 mm by ERT systems. Concrete mixture with a water to cement ratio of 0.65 was used in this study. Prism specimens were cast with cross-section of 330 by 330 and thickness of 50 mm as shown in the figure. It is noted that stainless steel electrodes were embedded by inserting the electrodes with diameter of 1.4 mm and with a depth of 10 mm before casting. In addition, the electrodes in the specimens were fixed using conductive epoxy to reduce the contact impedance. The distance between two electrodes were consistently 30 mm in each electrode. It should be noted that two duplicate specimens were made to confirm the consistency of the results of ERT measurements. The specimens were exposed to room conditions controlled at 20 degrees Celsius, and the ERT measurements were carried out, which served as reference data. And then the specimens were immersed in water tank up to the depth of 110 mm as shown in the figure. As can be seen in the figure, the saturation degree of water increased by absorbing water from the exposed surface for a week. And then AC current was injected to a pair of electrodes selected among 30 electrodes, which was carried out by adjacent stimulation pattern. Subsequently, potential differences were measured using tester in each pair of electrodes. This figure shows the results of potentials measured on the electrodes embedded in the concrete specimens. The measurements were carried out before case 1 and after case 2 immersed in water tank. As can be seen, the potentials measured in case 1 ranged 0.1 to 0.2 volts on average, while the potentials were observed to be smaller than 0.01 volt in most of the measurement cases in case 2. However, larger potentials compared to those observed in case 1 were clearly observed in some cases. Those were potentials greater than 0.3 volts. In general, potentials could be smaller in the case of saturated concrete owing to smaller resistivity associated with poor solutions with higher conductivity. However, some cases registered larger values, although water absorption took place around the depth of 110 mm. The variation of potential between case 1 and case 2, subtraction of case 2 from case 1 was calculated and shown in the figure. In most cases, the variations for positive values start suggesting that the potentials change to smaller potentials owing to water absorption. In contrast, some results were observed to be negative values, which could be attributed to dried regions deeper than 110 mm away from the exposed surface. The effect of resistivity distribution, which is essentially modified by absorption water, on the potentials measurements was analyzed by FEM simulation in the next. This figure shows the comparison of potentials measured in the case 1 and case 2 respectively. As can be seen, the variation of potentials was clearly divided into two cases in which the potentials changed to larger or smaller values in each case. The measurement cases pertaining to each tendency can be distinguished based on the locations of electrodes. The lower potentials in the cases of 6 to 25 electrodes were found to be consistent with the permeated region by water absorption, which is observed to be deeper than the immersion depth of 110 mm actually. The permeation front could be varied between 120 to 150 mm. The locations of electrodes 6 and 7, 24 and 25 respectively. In contrast, the potentials measured on the electrodes 1 to 5 and 26 to 30 were clearly larger compared to those observed before the immersion in the experiments. This study employed sensitivity analysis on the water permeation in concrete on ERT measurements as mentioned previously. FEM program using MATLAB was used to model the dimensions of concrete specimens and mesh sizes 0.5 mm to analyze the gradual increase of permeation front of water. The FE model analyzed in this study was shown in the figure, and the potential distribution was calculated based on Poisson equation when unit current of 1 mA was injected in each pair of electrodes, and then the potential differences between the remaining pair of electrodes on the surface of electrolytes were calculated. The number of elements was 16,271 and the electroresistivity was set as about 500 ohm-meter for water saturated region and about 1,100 ohm-meter for partially dried region. The gradual increase of permeation front was modeled by changing the electrical resistivity in the elements in which the electrolytes were shown to be fully saturated. This figure shows the results of potential differences in each measurement case calculated based on potential distributions in electrolytes by FEM. It should be noted that the results of case 2 were the potentials calculated when water permeation took place up to the depth of 140 mm as discussed previously. The potentials were observed to be lowered in most cases as shown in the figure, which is consistent with the results observed in the experiments. As mentioned previously, the potentials of electrodes located in dried region which is not reached by the water absorption water were changed to larger values which could be attributed to sudden changes of electroconductivity in concrete. This could have large influences on the current flow and potential distribution when current was injected. The potential difference between case 1 and case 2 was shown in the figure on the left-hand side based on the sensitivity analysis. The potentials calculated on the electrodes 6 to 25 were similarly lowered, although the variation is prominently smaller. In contrast, the potentials in the dried region were marginally larger compared to those of case 1. It should be noted that the potentials calculated on the electrodes 1 to 5 and 26 to 30 were found to be lowered by the sensitivity analysis, as can be seen in the figure in the middle. When the current injection was carried out on the electrodes located in the saturated region. In contrast to the results, the experimental results corresponding to those potentials simulated by FEM were mostly not lowered as shown in the figure on the right-hand side. This draws the distinction between experiments and FEM simulation in that the potential in the dried region was largely influenced by the dried surface, especially in the experiments. This led to larger variations between experiments and FEM simulations in terms of the increasing or decreasing tendency of potentials caused by the absorption of water. Next, the permeation depth was assessed by ERT simulation based on the two data sets, although the measurement errors and noises are present in the current testing setup. This slide shows the results of ERT measurements and reconstructed images. In particular, permeation front is central in this study. By analyzing the two data, case 1 and case 2 as an inversion problem, the variation conductivity distribution owing to water absorption is reconstructed with respect to the changes of electrical resistivity. It should be noted that ERT employs the difference imaging methodology, which is advantageous in assessing the spatial changes of electroconductivity in two measurement timings. This figure shows the results of potential measurements up to 300 measurement cases. As can be seen, the variation in each measurement was observed to be larger and highly scattered in the case of case 1. In contrast to the results, the potentials were found to be stable at lower potentials when specimens were immersed in water tank. The presence of water significantly modifies the ion movement associated with ion conduction in concrete. As can be seen in the figure, the movement of water in concrete took place by absorption of water, which can be highlighted in the dark color by visual observation. And the results of ERT based on the reconstructed images were found to be reasonably consistent with the visual observations made on the surface as shown in the figure. It should be noted that the unsaturated region could have relatively lower moisture content, which led to unclear permeation front between fully saturated and relatively dried regions. Based on the results obtained, the ERT system could be useful for assessing permeation front, although moisture distribution comprised of unsaturated and dried regions is present in the concrete specimens. This is highly advantageous when assessing actual concrete members. This study examined the ERT assessment for water absorption in concrete prism specimen, which is not typical application of ERT system. From this study, the results indicated that the region with higher conductivity estimated in the saturated regions is evidently in good agreement with permeation front of water observed in the experiments. This study has provided the important insight that water absorption in actual concrete members could be assessed by the electrical measurements. Thank you for your kind attention.